Hello again, Nick Leifker here, and welcome again to Operations Management. So far in forecasting, we've talked about what makes a good forecast. We've talked about various types of forecasts. We've talked about simple forecasting techniques such as naive forecasting and moving average and exponential smoothing. We've talked about more complicated techniques such as trend lines, such as multiple linear regression. What we're going to do with these forecasts is ultimately we need to see how well they perform. So how do you measure how well a forecast works? Well, there's several tools that we have available to measure forecast accuracy. The first, mean absolute deviation. What mean absolute deviation is? It's simply the average distance from the correct result. In other words, what's the average amount that a forecast is incorrect, is wrong? So what's the average error? The second, mean squared error. What we do is we take those errors that I was talking about before, the amount that it's wrong each time, and we square each of those. And then we almost find the average of it. We don't quite use the average. There's a quirk that I'll talk about with regard to the formula and why it's there, but I'll talk about that in just a couple of minutes. But think about the result of squaring these errors. Suddenly, large errors have a much greater impact on our error measurement. So if we square the error, well, under mean absolute deviation, then that would, if the error were twice what it normally would be, well, that would cause a mean absolute deviation to be twice that initial amount. However, with mean squared error, if our error is twice what we normally would expect, then mean squared error will penalize that 4 times as much. That's what mean squared error does. That's what mean squared error focuses on. It penalizes for these large errors. Now the third, mean absolute percentage error. What it does is it takes those errors that we found with mean absolute deviation and it divides them by the actual result so that we find the percentage error each time. And we take the average of those, and from that we find the average percentage by which each forecast is incorrect. What mean absolute percentage error does is it allows for the comparison of forecast accuracies for two different forecasts that forecast for two different things. For instance, we might have a forecast for temperature and a forecast for humidity. Well, if we wanted to compare how well those two are doing, well, we'd have to decouple it from the initial item that we're forecasting. We'd have to somehow decouple it from temperature. We'd have to somehow decouple it from humidity and turn it into a percentage. And that's what mean absolute percentage error allows us to do. It turns this value for error into a percentage for error. And thus we're able to compare it to other forecasts that forecast other quantities. So, why would we choose mean absolute deviation? Why would we choose mean squared error? Ultimately, what we choose with regard to which forecast accuracy measurement we use is the penalty for being wrong. What is the penalty for being very wrong as opposed to being just a little wrong? For instance, suppose the penalty for being wrong is a lost sale. In other words, the penalty, if we're off by 4 in our forecast, then we lose 4 sales. If we're off by 2, we lose 2 sales. So that's a linear relationship, right? That's a proportional relationship. In that case, what we would want is we would want mean absolute deviation because in that case, the penalty is proportional to the error. In other words, twice the amount of error we have, then that means twice the penalty. On the other hand, sometimes there are cases where the penalty for being wrong for being a little wrong is almost negligible. But after a point, the penalty for being wrong skyrockets. A good way of thinking about this. We try to match Oregon donors to recipients. And to do that, we would use all sorts of variables in our model. Well, if we're just a little wrong on matching organ donors to recipients, well, what happens? Well, almost nothing. In that case, the operation is a success, the organ transplant works, and the patient hopefully makes a full recovery. However, after a certain point, if we're too far incorrect, if we have too much error, what'll happen? Well, the patient will reject the donated organ and will be in far worse shape than they would have been before. So what happens to the penalty here? It goes from almost nothing to almost everything in a very short period of time. Well, in that case, where we have this significant ramp up for error after a certain point, well, in that case, we'd want mean squared error, because that's what mean squared error does. After a certain point, because it penalizes the errors squared, it squares the penalty for these errors. It significantly penalizes for larger errors. And so smaller errors have very little effect on our mean squared error result, but larger errors have the bulk of the results for mean squared error. And as for a mean absolute percentage error, well, with mean absolute percentage error, if we are going to use this particular this particular error measurement to compare a forecast method with another forecasting method that measures something else, as I mentioned before, temperature and humidity, well, then we would want mean absolute percentage error so that we decouple the error measurement from whatever it is that we are measuring. In other words, we put it into a format that can be compared across platforms, across forecasts. Now, here are the formulas for each of these. Now, don't be intimidated by the math. I'll explain. The math looks complicated, but it's actually a lot easier than it seems. First, that Greek symbol, that's sigma, that's sum. So, what does this mean for, say, mean absolute deviation? Well, for each forecast and actual result pair that you have, you find the error. Actual minus forecast. You take that error. And then you take the absolute value of it. That's what those two vertical brackets mean. It means absolute value. So that is the magnitude of a number. So the absolute value of, say, -5 is 5. The absolute value of 6 is 6. So if there's a negative number there, you just drop the negative. That's what that means. So you take these error measurements. You take the absolute value of them. Essentially drop the negatives from any numbers there. Then you sum them up. You add them up. And then you divide by the number of measurements. That's mean absolute deviation. It's simply the average error. Now, the second, mean squared error, well, you find that error, actual minus forecast. And in this case, you square it. So if you have an error of 2, you square that to 4. If you had an error of 8, you'd square that to 64. You sum those all up, and then you divide by the number of measurements minus 1. So there's a reason why the n minus 1. And that is because of that square in that formula, we lose 1 degree of freedom. And degrees of freedom is a complicated concept in mathematics, but by losing that 1 degree of freedom, if we divide by n rather than n minus 1, what we end up having is what's known as a biased estimator. In other words, our estimate of the mean squared error would actually depend on the number of measurements we have. And what we prefer is what's known as an unbiased estimator. In other words, an estimate for the error that is not dependent on the number of measurements we have. So to make sure that mean squared error is an unbiased estimator, In other words, that it isn't affected by the number of measurements we have. We divide by n minus 1, the number of measurements minus 1. So, because we want an unbiased estimator in this case, what we do, we take that error for each forecast and actual result pair for each measurement. We square each of those, we sum those up, and then we divide by the number of measurements minus 1. Now, with mean absolute percentage error, well, you recall when we were talking about mean absolute deviation that we would find the absolute value of each error. In other words, we'd take the absolute value of each error. Well, we can use that data again to find the percentage error each time. So we take those absolute values we calculated before each time, and we divide it by the actual each time. So, actual minus forecast, in other words, the error. Take the absolute value of it, so if it has a negative, it drops off. And then you divide by the actuals. And there's a very good reason why we use the actuals rather than the forecast. To divide by, I mean. Where does a forecast come from? Forecast comes from us. It could come from anywhere. You know, we could pull a number out of a hat and have that be a forecast. But that may not be a good representation of reality. Actual results, they're a good representation of reality. So we divide that absolute value of the error, divide that by our actual results each time. So we find the percentage error with each measurement by taking that error divided by our actual results. We then sum those up, divide by the number of measurements, and that gives us the mean absolute percentage error. So, to demonstrate these, well, here's an example. We have 6 pairs, 6 measurements. We have 6 forecasts, 6 actual results. So actual sales for week 1 are 15. Our forecast for that week was 17. Actual sales for week 2 is 19. Our forecast for week 2 was 18. So we have actual sales and forecasted sales for 6 weeks. So based on this, how well is our forecast doing? Well, let's first look at mean absolute deviation. Let's look at MAD. So for each week, what do? Well, for each week we take actual minus forecast. So for week 1, 15 minus 17, that's negative 2. 19 minus 8 for week 2, 19 minus 18, that's 1. We then take the absolute value of that number. In other words, if there's a negative, we drop it off. So the absolute value of 15 minus 17, well, that's 2. The absolute value of 19 minus 18, that's 1. Of course, the absolute value of 18 minus 18, that's going to be 0. Absolute value of 15 minus 17, again, is 2. So we calculate this error for each time period, for each week. And then we take the average of those. In other words, we sum those up and divide by the number of measurements, the number of error measurements that we have in this case. So, for our mean absolute deviation, 2 plus 1 plus 0 plus 2 plus 3 plus 3, divided by 6, well, that's going to be 11 over 6, so that's 1.83. So our mean absolute deviation for this forecast is 1.83. So, how about mean squared error? Well, we found those errors before, actual minus forecast before, right? So, in this case, for week 1, actual 15, forecast is 17. Well, the beauty is that no matter how we handle this, the square of any number is going to be positive. Unless, of course, you have imaginary numbers in there, but let's not get into imaginary numbers. That's math that we should not deal with right now. But anyway, so should be negative 2 squared. Well, 2 squared, it's the same either way, it'll be 4, right? So you take those mad results that we got before, those error results we got before, and you square those. So for week 1, the error was 2. 2 squared is 4. For week 2, the error was 1. 1 squared is equal to 1. For week 3, the error was 0. Well, 0 squared is 0. By the way, if you ever want to have an interesting mental exercise sometime, consider what 0 to the 0th power is sometime. Just something to think about. The question is it 0 or is it 1? But anyway, just something to think about. But going on, 2 squared, our error for week 4, our error for week 4 was 2. 2 squared is 4. For week 5, 3 squared is 9. For 6, 3 squared is 9. What we then do is we then take those squared errors, sum those up, so 4 plus 1 plus 0 plus 4 plus 9 plus 9. And then we divide by the number of measurements minus 1. So there were 6 measurements, 6 minus 1 is 5. So in this case, those summed errors come up to 27. 27 divided by 5 is equal to 5.4. So our mean squared error for this measurement is going to be 5.4. So how about mean absolute percentage error? Well, we found those errors from before, right? Those absolute value of the errors from before. So we can use those again. Well, 15 minus 17, that's going to be negative 2. Absolute value of that is 2. 2 divided by 15, that's going to be about 0.13. Again, make sure you're dividing by the actuals. You don't want to be dividing by the forecast here. Make sure you're dividing by the actuals for each measurement. So for week 2, absolute value of 19 minus 18 is 1. 1 divided by 19, that's 0.05. For week 3, well, absolute value of 18 minus 18 is 0, so we're going to get 0 here. For week 4, absolute value of 15 minus 17 is negative 2. Well, negative 2 divided by 15 is 0.13. So we calculate this percentage error for each week. Once we have that for each week, we find the average of all of those measurements. So 0.13 plus 0.05 plus 0 plus 0.13 plus 0.23 plus 0.25. We sum those up, divide by the number of measurements, divide by 6 in this case. We get a mean absolute percentage error of 0.13, or 13% if you like. So, with regard to forecasting, well, a few things to remember. First, forecasting methods are only as good as the level to which the current data, past and present, reflects future events. If the past and the present don't reflect the future, then it's not going to be a good forecast. Second, forecasts are almost always wrong. We talked about why. Variation happens. As a result, we have to be careful about that. We have to take that variation into account when we are making our forecast. Then we have types of forecasts. We have things like judgmental forecasts, where we get opinions from experts, people who are involved with regard to this item that we're trying to forecast. We have time series forecasts. These tend to be the simplest. Here we just assume that history is going to repeat. We take past data and we project it into the future. And then there's associative forecasts. And here what we try to do is we try to get to the root causes of our results. So we try to find an algorithm, a formula that explains our results by using things that affect those results. We then looked at all sorts of methods of forecasting. We very briefly looked at exponential smoothing with trend. Again, it's not the best of tools. Just know it exists. Know that it's a forecasting method that allows you to forecast for trend. Also, we looked at things like seasonal indices, and then we looked at the various forms of regression. First, linear regression, which is just our trend line, and then, of course, multiple linear regression and its various uses. And then we finished off by talking about forecasting accuracy. How do we measure it? under what circumstances do we use each tool, and of course how to calculate them. So we talked about mean absolute deviation, which is just the average error. We talked about mean squared error, which is somewhat of a measurement of the square of each error. And then, of course, mean absolute percentage error, which is a measurement of the average percentage that each forecast is wrong. So that is the end of the slides for this week. Next week, we'll start talking about the process, how to diagnose it, how to fix it, how to improve it, how to make sure that we have a good process. So that is what is coming up next week. Until then, be well, take care, and have a good week.